Okay, I think I just begin. First, let me apologize because I had indicated earlier that we were going to have a physical class today. However, over the weekend, I developed a flu, so I don't think it would be proper to attend the class physically because then I might transmit the flu to other people, undeservedly so. So I decided that we just have the online class and hopefully we can resume next week physically. Secondly, the class rep indicated to me that you had discussed and agreed that you want to sit your CAT on the 4th of November, which is next Monday. So please, let me use this forum to confirm that we are going to sit our CAT on the 4th, which is next Monday, at 8 a.m. in the morning during our usual class. So please share it widely with your colleagues that there's going to be a CAT next Monday. I do not intend to provide any supplementary CATs or any other CAT for that matter. So please just indicate to everyone that everyone should attend and sit, and everybody should be available for the CAT on Monday. So that's very critical. I will not set another CAT after the one that will be done on Monday. Now that CAT is going to be basically on what we have discussed on the first topic, and the first topic was root locus. So everything from the beginning of the root locus to the last class that we had on root locus, that is expected to be tested in your CAT. So in your preparation, read the first topic, very important. So having said that, I hope it's very clear and you will help relay that information to the others. I will therefore have to proceed to a different topic, which is going to be the subject of our discussion. I intend to be very quick on this one because most of the concepts around this one you have done before, especially in the fourth year studies. So I should not be taking too much time explaining certain concepts here. Now, there are certain requirements for this. I think I'll mention them as I speak, and then so I hope you'll take note and then prepare adequately so that we quickly rush through state space representation, which is basically modeling in the time domain, and then I move on to the last topic before you sit for your exams. Okay, so typically, forgot to share my screen. I see a hand already up. Where? What's up?
Yes, I wanted to ask, will the cut also cover the compensators?
Yes, I just indicated, ladies and gentlemen, I've indicated that the CAT is going to cover everything that we have discussed up to the last class. Everything on root locus, basically everything on root locus and the design or modeling using the root locus technique. Everything. So please prepare adequately for that. So that means it includes compensators, because compensators are basically the design elements using root locus. So the CAT is going to cover everything up to the last class. What it will not cover is what we are going to start discussing today. I hope that's clear, Were.
Yes.
Okay. Any other questions or concerns before I begin? Good. Okay, so let me begin with the discussion on state space representation. I was just about to share my screen. Do I even have a screen to share today? Oh, okay. I think, sorry for scrolling too much. I forgot to put this in the right perspective. These are previous notes. Okay. So let me just say state space representation. So our discussion is going to be on state space representation. I need to make this bigger. Okay. State space representation. This is going to be our topic, new topic. Now, other books generally say that this is modeling in the time domain. Now, the reason we are calling it modeling in the time domain is because there are other modeling techniques, and we have just covered one already. So there are usually two approaches when you want to design or even analyze feedback control systems. So in the design and analysis of feedback control systems, we have two approaches. Now, people who come late, they want to be admitted instead of coming in early. So in the design and analysis of feedback control systems, we have two main approaches, okay? These two approaches are, you need to have the classical technique or the first technique, which is known as the frequency domain technique. The frequency domain technique. It's the good old method, okay? Or what we're calling the classical method. And in the classical method, this is where you take your control system, you convert the system's differential equation into a transfer function. So once you convert the system into a transfer function, you generate a model, a mathematical model for that system. And that model is going to be able to relate the input to the output, meaning it's going to be a representation of the output of that system based on the inputs. Okay, that is the frequency domain. In fact, this is where we had our root locus. So root locus is basically a frequency domain technique, because it is a technique where we convert a system into a transfer function that therefore helps us model the relationship between the input and the output of the system using a mathematical model. Okay? In fact, the objective of frequency domain techniques are the main advantages or the main objectives of the root locus, and that is one, for those who remember, is to achieve stability. That is an important objective. And the other one is for us to get the transient response or improve on the transient response. Okay? So these two are usually the main objectives or the main goals that drive the use of the frequency domain technique. It's the good old method. It's commonly used. The problem with this technique, or basically I would say the problem with root locus, is that yes, they give us stability. Yes, we are able to analyze the system's transient response, but we cannot apply it in several systems, especially because this system is only, so the main disadvantage here is that this system disadvantage is limited to linear time invariant systems. So basically, you can see that all the transfer functions that we were analyzing previously using root locus are linear time invariant systems. I don't think at this stage I should be able to define linear time invariant systems to you. If I have to, then there's a problem somewhere. So I hope by now you know what linear time invariant systems are, you know what causal systems are, and so on and so forth. So that means this system is limited in its application because we can only apply it to a linear time invariant system. Therefore, there is need to generate another system or come up with another technique for designing and analyzing control systems. And that is what we are going to look at today. So we have another technique, which is now a time domain approach So you have a time domain approach or a time domain technique. Okay. Now, this is what we are referring to as state space representation. State space representation. Okay. So whereas frequency domain techniques was basically root locus method used to achieve stability and improve on the transient response of your system, it is limited only to linear time invariant systems, and therefore we cannot apply it in several other areas like systems that have multiple inputs and multiple outputs. That means there are a lot of connections between the input and the output. We cannot use root locus in such systems. Those systems are considered to be more complex, and so root locus cannot give us a proper modeling technique for analyzing that system or even designing it. Okay, so that's why we come up with the time domain technique, which is a state space representation technique. So this is another method that now we can use to analyze and design more complex or more complicated systems. So this technique is, let me just say, used to analyze and design more complicated systems. Such as MIMO systems. I hope by now you know what MIMO systems are. And so because you can use it for MIMO systems, you can even use it for the simplest of a MIMO system, which is a SISO, a single input, single output system. So that means you can compact a MIMO system and represent it in state space with the model similar to the one that you use for a single input, single output system. Meaning, time domain techniques like state space representation are able to represent MIMO systems in a more compact manner. Makes them look simple, just like a single input, single output system. Okay? So this system has several advantages, actually. The use of state space representation has several advantages, key of which is we can use it to represent more complicated systems that I have already indicated. Then this approach, the time domain approach, can also be used to represent systems, with a digital computer. Meaning, if you want to represent systems that require digital simulation, okay? So let me just say model systems for digital simulation. You will use the state space representation method. The reason for that is you'll notice quickly that state space representation method involves the use of matrices. So you're going to transform the control system, the feedback control system, and represent it not as a transfer function, but as a matrix. And so it's easy to model systems in MATLAB or in Python or in Java when the system is represented as a matrix. Because you can imagine inputting matrices in the system is very easy. In a digital system is very easy. Okay, so this system is very critical in such cases as digital simulation systems. Okay, the approach is also used because it's very it's applicable, or it's attractive to systems that require software packages. So I would just say the other advantage is that you already have numerous software packages are available. Software packages are already available. Okay? For state space representation. And this is a good advantage because representation. This is a good advantage because we have already set space representation. We have already developed softwares that help you model systems using state space representation or analyze systems using state space representation. And because there are several of them, you're spoiled for choice. So you can use whichever technique or whichever tool you'd like to model your system using state space representation. And that gives it an edge over the classical method, which is the root locus method. So it's very important that we consider state space representation as a technique that will help us analyze complex systems, digital systems that require digital simulation, or systems that require us to obtain quickly some software packages that allow us to do the representation. Okay. All systems, and this is also another advantage I would say actually, all systems or all feedback control systems that can be modeled using the frequency domain can also be modeled using the time domain. So I could just say all systems, let me just say control, all control systems that can be modeled using frequency domain techniques can also be modeled using time domain techniques. And the reverse is not necessarily true, meaning that the control systems that you can model using frequency domain, you can still use state space. But systems that can be modeled by state space, not all of them can be modeled using the frequency domain techniques. A good example are the MIMO systems that I've told you. You can't use root locus or classically what we are talking about as the frequency domain technique to model MIMO systems. We generally would go for state space. But if a system can be modeled using frequency domain, it definitely can also be modeled using time domain. And that's another very good advantage of, so it's sort of like, it's a very versatile approach, okay? So we can apply it in a wide range of systems. But it also has its own disadvantage. We must say, we cannot say that it's only just advantageous. So what's the main disadvantage of this system? We have agreed that yes, we can apply it in a wide range of systems. But one, it is not intuitive. It's not very intuitive as the frequency domain approach. As the frequency domain approach. You remember that when we were designing systems, or even when we were analyzing systems using root locus, when we wanted to represent a system using root locus, you could relate the system's both stability and transient response step by step. You could actually envision or picture that system because of the graphical nature. Because of the graphical nature of root locus. The root locus is a model that gives you a graphical representation of how the system is behaving. So even in your design, you have like a graphical picture of how you want the system to behave. But in the problem with state space representation, it's basically matrices. So if it's a matrix representation, they're basically figures. So looking at the figures is very abstract. It cannot really give you a picture of the system by looking at numbers. Whereas in the frequency domain technique where we were using root locus, you could picture a system as it moves, as the gain increases towards infinity. You could see how the poles are actually moving their trajectory. And you could tell even areas where the system are marginally stable when it's crossing the J omega axis, and so on. But using state space representation, we cannot tell that information because we'll be representing the system just using numbers in matrix forms. So that's one disadvantage of this system. The other disadvantage of this system is that you require, I would not say rigorous, but you require a good amount of calculation. So numerous calculations need to be carried out. To interpret the model. Whereas in the frequency domain technique, we were just doing a few calculations. You could even sketch the root locus without doing any calculation. But here you have to carry out a few calculations. Okay. So I've spent a lot of time introducing this just to, let you know the relevance or the importance of state space representation techniques. Now, we are going to go into the real thing now and see how we can now start analyzing and even later design systems using state space representation. However, and this is one of the points I needed to mention to you, I expect you to review your knowledge on matrices. For me to move fast enough, I shouldn't be telling you now how to calculate the inverse of a matrix, for example. That I expect you to do. I shouldn't be telling you how to represent the input and output of a system, that is the transfer function of a system, using matrices. That is information that you should basically have already. So the design here relies heavily. So state space representation relies heavily on matrices, okay, and their operations. When I say and their operations, I mean adding, subtracting, getting the adjoint and stuff like that. So please just review your knowledge on matrices so that you are up to speed, because I will not be explaining the concepts of matrices. I will actually just strictly focus on the analysis and design elements of our model. So please do that. Now, quickly, because of time, I move to some common definitions that we are going to use. There are some terminologies that we are going to be applying here, and I expect you to understand them as we go along. So one of the most common ones are, we have something called a state. Because remember, we have just said state space representation. So what is the state? Okay. So the state is simply as the smallest set of variables, the smallest set of variables. That's called a state. Actually, we call them state variables. Okay. So by having knowledge of these state variables and the knowledge of the input, you can know the behavior of the system. So for you to analyze the behavior of a system at any given time, you must know the state variables, and you must also know the inputs. So if you're given the inputs of a system and the state variables, then you can be able to tell or determine the behavior of the system. So we also have what we call a system variable. Now, students confuse between state variables and system variables. So a system variable is not the same as a state variable. I've just said that a state variable is the smallest set of variables that we are calling the state variables. But a system variable is any variable that responds to an input or responds to an initial condition of the system. So I would just say this is any variable that responds. I'll just go quickly through this. I think I'll give you more notes later. To an input that responds to an input or initial conditions. Okay, that is a state, sorry, a system variable. So the state variable itself, the state variable is the smallest set of linearly independent systems. So this is the smallest set of linearly, and this is a very important element, linearly independent. Because in most cases, it will be left to you to determine what the state variable is. So I'll give you a system and I'll tell you to identify state variables from that system. So you should know that you should be looking for the smallest set of linearly independent system variables. So it means you get your state variables from the system variable. You get your state variables from the state variables. Now, we also have a state vector. Now, this should be very easy because now it's a vector where the elements within that vector are state variables. So this is a vector whose elements are state variables. So for example, I will tell you, look at a pendulum system. In a pendulum system, what do you think are the system variables in a pendulum? A system variable, we have just said, is any variable that responds to an input or an initial condition. So if I move the pendulum to one end and then I let it start oscillating, what are the variables? Is it velocity? Is it acceleration? You know, is it the position? Okay, those are, you have to define the state variable. Those are the state variables. It's the smallest set of linearly independent systems. I'll tell you what linearly independent systems means for those who don't know. So if you put those variables in form of elements, then you form a state vector. Okay, so there are other definitions that I think I'll just provide in your notes. The two main ones that I need us to also just define before I start with examples is state equation. This is a very important equation. So the state equations, because it's usually is a set of simultaneous equations. A set of simultaneous equations. And how do you get it? They are usually first order, actually. First order. Simultaneously, say the simultaneous differential equations. They are differential equations. Okay? So in this equation, it's the variable that you are solving are the state variables, meaning the equation has to be the state variables equals to something. And I'll give you an example to see. And then you always have an output equation. Now you'll always see, because it's an output, the output is always one. So you can't have output equations. It's an output equation. But the state can have more than one equation because it's simultaneous equations, differential equations. But the output is always just one. So this is an algebraic equation that expresses the output, variables, expresses the output variables as a linear combination, of state variables. I'll give you an example, and inputs. And inputs. So I think we're progressing well. Yeah, good. So now, these are some of the, then only terminologies we'll be using, but there are some of the terminologies that we'll be using quite often. And so I expect that you sort of acquaint yourself with most of them because you're going to use them. I told you state space representation is all about matrices. So how do we represent systems in matrices? And you'll notice that in most cases, every state space or every feedback control system can be, you can write a state equation for that system and also the output equation. So we have a general format for writing the state equation and the output equation. So if I ask you to represent a system using a state space model or a state space technique, I expect you to write the state equations for the system and also write the output equations for the system. And we'll look at practical examples of those, okay? So let me just say state space representation. How then do we represent systems using state space? So any system can be represented using two equations. One is, so let me just say a system is represented in state space by one, we say that the derivative of the state vector is given by ax plus bu. Now, please note, all these are vectors. There's no scalar quantity here. All these are vectors. So some books will use bold letters to represent them. Some books will put like a heart over each of them. But please just know all these are vectors. And then the output equation is given by, I mean, these are vectors or matrices because you remember, if I have the capital letters, so matrices are represented using uppercase. So let me not say capital letters, let me say uppercase. And vectors are represented using lowercase. Okay, that's what I'm saying. So every system must be represented in this format where you have 1A and 1B, okay? All the systems. So X is the state vector. And of course, X dot is the derivative. Of the state vector. And it's a derivative with respect to time. It's a derivative with respect to time. Y is the output vector. Y is the output vector. Please remember this because every system that we are going to model in state space will be written in this format. Of course, U is the input. Other books call it control vector. Okay, so I've defined all the vectors. How about the matrices? A is known as the state. Other books will call it a system matrix. Okay, B is the input matrix. And then C is the output matrix. And lastly, D. It's not very common in certain systems, but it might be available in other systems. Some books call it feed-forward matrix, feed-forward. Others call it direct transmission matrix. Okay? So this first equation here is what we're calling the state equation. Very important. Okay? Remember, it consists of the state vector, that is the state equation consists of the state vector, and it also contains the state variables. That's why it's called the state equation. It has the state vector, which contains the state variable. Because the state vector is written, the elements of the state vector are the state variables, okay? Which we'll see how we can solve. The second question, or equation, sorry, is the output equation. Output equation. So all systems have to be represented in form of the state equation and the output equation. Remember, the state equation has the derivative of the state vector. So don't forget that derivative. Now, it is also important to mention that it is critical for you that in the choice of the state variable, there's not a unique way determining the state variables. Remember, we have said that the elements, if you have the state vector, so let's say it's a vector like that, A, B, C, D. These elements here are the state variables. Okay? But there is no unique way of determining the state variable. But there's a rule for determining the state variable. Meaning, two students can pick two different state variables and are both correct, as long as they follow the rule for determining or for choosing the state variable. And that rule is that state variables have to be linearly independent, and you have to pick a minimum number of them. So there are two main rules for choosing the state variable. Okay, so I'll get back to that, but please note that, let me just indicate here, the first step in representing a system, is to select the state vector. That's the first step. You have to select the state vector. And the state vector comprises the state variables. Okay, so I'll just write in bracket comprising, or whose elements are the state variables. Whose elements are the state variables. Okay, so that you have to do. Oh, let me just say comma, which must be chosen according to the following conditions. Now, number one, the condition, because the first step we take is to come up with a state vector. The state vector consists of the state variables. So how to pick the state variables? Number one, there must be a minimum number of state variables, a minimum number of state variables must be selected as components or elements of the state vector, as components of the state vector. Very important condition. But the minimum number that you're selecting must be a sufficient number to completely describe the system. Because if you don't pick a number that is sufficient to describe the system, then your system will not be completely represented. So you have to pick a minimum number that completely or sufficiently describes the system. I will give you techniques of knowing how many or what is the number that I must pick for any control system that has a transfer function. What is the number or the minimum number that I can pick that sufficiently describe that system? Number two, not just selecting the minimum number, the components of the state vector. That is, this number of state variables. So the state variables, let me just say the state variables must be linearly independent. Very, very important point. Must be linearly independent. So somebody again is asking, what are linearly independent variables? Okay. We have just said that these state variables, which are the state vector, must be linearly independent. Okay. So let's say you had a state variable x1, x2, x3. That is, a system has the state variables x1, x2, x3. If x3 is, for example, equal to 2x1 plus 3x2, meaning you are able to represent x3 as a combination of x1 and x2, it means that x3 is not linearly independent. So because the condition is for us to come up with a state variables, we have to pick a minimum number of state variables that completely represent our system. But these state variables must be linearly independent, meaning we cannot express them as a function of other variables. So like I've told you here, because I am able to express x3 as a combination of x1 and x2, then that disqualifies x3, because then it means x3 is linearly dependent. It's linearly dependent on x1 and x. That's why I'm able to write it in the form of x1 and x2. So it's depending linearly, because you can see the coefficients are just constants. They're linear. Okay. So the x3 not qualify in this case as a state variable that we are going to use. Okay. So the knowledge of x1 and x2 can give me x3. So that is not required. That means it is linearly dependent. So the variables that you're picking are such that you need knowledge of those variables, and they cannot be obtained by knowing other variables. You see, I only need to know what x1 is and what x2 is for me to know what x3 is. So that means x3 is linearly dependent. But that's not what we want. We want to pick state variables such that we cannot describe those state variables as a combination of any other variables. So it's like basically saying we actually need the knowledge of those variables for us to proceed. We cannot derive those variables from other variables given. Okay, I hope that's very clear. Let me give you another example. If you want the voltage across an inductor, common, it's always L di L dt. Okay, so we can say that the voltage across the inductor is linearly independent. So VL is linearly independent of IL. Meaning, for you to obtain VL, you have to differentiate IL. That's another hint that state variables can also be obtained by getting the derivative of other variables. So for example, if x1 was a variable, then the derivative of x1 is also a variable. The double derivative of x1 is also a variable, a state variable, because they are linearly independent. Because the rule in maths is, if you get a variable and its derivatives, they are all linearly independent. Okay? Because in this case, you cannot evaluate VL as a linear combination of the current IL. That's why we are saying VL is linearly independent. Okay? That is to say, in other words, and in simple terms, you cannot obtain VL, yeah, by just without obtaining what I is. So you need knowledge of IL. So VL is linearly independent of IL. I'll give you several techniques also of determining what state variables to pick. But like I told you, there's no one formula for picking a state variable. It's just like what we were doing in modeling, that there's no just one technique of doing it. You can use several methods, but you arrive at the same solution, okay? So in this case also, we can have several techniques of picking the state variables, but the solution will always be the same. Please remember the two rules. We have to pick the minimum number of state variables, and those variables must be linearly independent. We cannot express them as a linear combination of other variables. But also, we have noted that a variable and its derivatives are linearly independent. So this can qualify to be a state variable, this can qualify to be a state variable, this can qualify to be a state variable, because they are derivatives of each other. If, as long as they are derivatives, then you see they cannot be linearly independent. They are not linear in nature, okay? So the best way for us to do this is to go and obtain, do a few examples before it's almost 1 hour, so I need to finish these examples. But the last thing I need to state is, if I ask you, how do we know the minimum number of state variables to select? So you have given us a system, we've looked at it. How do I know the minimum number of state variables? Because the condition requires that we pick a minimum number. But how do I know the minimum number that is sufficient to represent the system completely? So typically, the minimum number that is required is equal to the order of the differential equation that describes that system. So can just say, typically, the minimum number of state variables, the minimum number of state variables equals, this is how you know the minimum number of state variables that you need for any system that you encounter. So that minimum number should be equal to the order of the differential equation describing the system. That is how you know. So if, for example, you have a second order system, then you know that you need 2 state variables. If you have a third order differential equation, So you have a third order differential equation that is used to describe the system. You need 3 state variables. Okay? That is important. Now, from the perspective of a transfer function, because sometimes we describe the system more often, I'll give you a transfer function instead of the differential equation. So if you have the transfer function, the order of the differential equation is usually the order of the denominator of the transfer function. So you have a transfer function, consists of a numerator polynomial or an equation and a denominator. So the order of this denominator, the order of the denominator is the one that is going to give you the number of state variables. In fact, it's the order of them, because sometimes the numerator can consist of after that's able to cancel out. So it's the order of the denominator of your transfer function after simplifying or after canceling the common factors. After canceling common factors. Okay? In the numerator, and the denominator. Meaning, after you have simply simplified your transfer function, then the order of the denominator becomes the number of state variables, the minimum number of state variables that you require. Okay, so you get a transfer function, first check, can I simplify this transfer function? That can I cancel out some common factors between the numerator and the denominator? Once you've canceled out all those common factors, whatever remains as the order of the denominator polynomial, that becomes your state variables. Now, another thing, which these are just techniques that you need to equip yourselves with. So I've told you how to determine the minimum number of state variables that is required to completely represent the system. But also, how do you pick the state variable in itself? You have a system, it's a pendulum. So what do I pick as the state variables? We've agreed that they must be linearly independent. That's fine. But how do I pick them? So again, typically, and this is just from experience, typically, state variables are chosen to be physical variables of a system. So the physical variables of a system are things like the position, okay? Because you can't represent the position as any other thing, position and velocity in a mechanical system. So those can form state variables. Especially, remember I told you that a variable and its derivative can form a variable. So if the position x can be a state variable. If I get the derivative of x with respect to time, I get velocity, can be a state variable. If I get the double derivative of x with respect to time, I get acceleration. That can be a state variable. So that is how we usually pick a variable. You take a physical system and its derivatives. That gives you the state variables. And you stop at the minimum number, which is the order of the denominator polynomial after simplifying your transfer function. I've spoken a lot, ladies and gentlemen, and we've spent 1 hour already. So I want to spend the next hour by doing examples. Some that will appear in your notes and some that will not appear in notes. So please take note. So let's do examples. That's the only way we get to learn much better than just providing abstract information. So the first example, example 1, we have a problem here. They say, given the electrical network, below, find a state. Sorry, guys. Sorry. I need to put this in silent. Okay, let's continue. Given the electrical network below, find a state. If the output, told what the output is, if the output is the current through the resistor. So we have been given a network. Let me draw the network so that we see it. So the network is basically this. We have a network here, a very simple network that we are used to meeting as electrical engineers a lot. It's an RLC network. So this plus, okay, let me write it properly. I have a plus and minus there. So here you have of course, the inductor, you have your resistor, and of course you have your capacitor. So let's call this V of T, voltage, supply voltage. Remember, this thing is with respect to time, so we're using small v, okay? Now, let's say the current flowing here through the inductor is IL of T, okay? So this is IL of T with respect to time. The current flowing through the resistor is also given there as IR of T, and of course we have the current through the capacitor as IC of T. Okay, so we have been told that the output is the current through the resistor. So the output is IR of T, we have been told is the output. Okay, so we have been asked to obtain a state space representation. I told you, if you ask for state space representation, it means you have to come up with two things. You have to come up with, so the question requires state space representation. That means you must come up with a state equation or equations, state equations, and the output equation is what is being asked here. You come up with the state equation and you come up with the output equation. Now, this is a work that you're come up. So, how do you go through this? So, step one, to label all the branch currents, the network, which I remember, you can label these currents to face whichever direction, as long as they will still obey the Kirchhoff's voltage law, or in other cases, the Kirchhoff's current law, you will still get the same answer. This by now, I am sure you know. Whichever direction you label your current to face, as long as you obey the law, the algebraic sum of currents entering a node should be equal to the algebraic sum of currents leaving that node, or the algebraic sum of currents at a node is 0. meaning the sum of currents entering plus the sum of currents leaving should give you 0 and stuff like that. So anyway, step number 1 is to label all the branch currents, which I have already done. Label all branch currents, and you can label them as you want. Okay. Number 2, like I told you, step number 2, the label is just for convenience. Step number 2 brings us to what was given here. And I wrote it here intentionally. The first step in representing a system is to select the state variables. That is usually the first step. So here we have to select state variables. And so here again is where you ask yourself, how do I pick the state variables? I already told you how to pick state variables and the number that you have to pick. If you look at your diagram, you will see that you have an inductor, you have a capacitor, and you also have a resistor. You've already been told that the output is considered to be the current to resistor. So we are not going to consider the resistor here for the state variables, because the resistor is going to be used to write the output equation. Because we've been told the output is the current through the resistor. So that is going to help us form the output equations. The state equations that involve the state variables are the ones that now we are going to use the inductor and the capacitor for that. So to obtain the state variables, because that's what we're going to use to write the state equations, we are going to use both the inductor and the capacitor. Meaning, and I told you, you can pick a variable and its derivatives for you to get that value that we are looking at. A variable and its derivative. So you simply look at your inductor and your capacitor, and you tell yourself, what do I pick between my inductor here and my capacitor? Okay? So in our case, we can decide by saying, I can pick the current through the capacitor, for example. Let me not write the T, because we already know it's just going to be tedious. We already know it's a variable. So what's the current through a capacitor? Remember, we've been told that the current through the resistor is going to be the output. So we are looking at state variables from our network that does not involve the current through the resistor. So we're just going to look at the current through the capacitor, which is the energy element, and also the current through the inductor, which is another energy storage element. So the current through the capacitor is going to be, typically, this you must know, is C dt. That's usually the formula of finding. And the current through the inductor is L it's usually L IL dt. Okay. So let me just call this equation 1, and let me call this equation 2. Okay. So we have to pick the state variables. So we have to pick the state variables. We have that are differentiated. Okay. Because a state variable,
Excuse
variable.
Sir. Excuse me, sir.
Is someone talking?
Yes.
Yes.
That equation 2.
Equation 2, yes.
I think we should be saying a VL or
Oh, thank you very much. Okay. I'm just talking too much here. I've made a mistake here. It's a voltage. It's a voltage, right? The voltage across the inductor is what we give by LDI LDT. Yeah. Sorry, thank you very much. Now, because now notice I'm not writing IL equals to, because then it would lead us to having an integral. Because remember, IL would now be 1 over L, the integral of VL dt. And I don't want integrals. Remember, we had said state variables should be a physical variable, and it also has its derivatives. So if there's a physical variable that has its derivatives, then that becomes our choice of the state variable. So in our case, I'm not picking IL because it would be an integral. It would not be a derivative. So that's why it's the voltage that has got the derivative in it. Thank you very much for that. That makes me know that you're observant. Thank you. So let's continue. So therefore, in this case, we have written two equations that simply are represented in the network. But now the question would be, out of these two equations, even in each equation, which do we pick as a state variable? The hint is you select a state variable as a quantity that has derivatives. Because remember, I had said if you take x as a state variable, then x bar is also, x, the derivative of x is also a state variable. The double derivative or the triple derivative, whatever, those are state variables. So one hint is to pick a quantity that has a derivative. So here we can select quantities. We can select quantities that are differentiated. Quantities that are differentiated as state variables, because they have their derivatives. So that makes it easy for us. So in our case here, we have ours as IL. No, is it the one that has a derivative? The first one is VC. The one that has the derivative is VC and IL. Those are the quantities that have a derivative. So clearly, you can see that our derivatives are picked from the right-hand side of our equation. We have picked them from the right-hand side of our equation. Now, the question is, can VC and IL be our state variables? Can VC and IL be our state variables? Please look at this. Because we have VC and IL on the right-hand side of our equation, it means that we can write what's our input here? Let me just check quickly my input. The input is the voltage. Okay, I think we can continue from okay. So now it's important. Let me just write this down. Since IC and VL, remember, I'm talking about this IC and VL. Since IC and VL are not state variables, because we can't have IC and VL are not state variables, because I said initially that we are able to express IC and VL in terms of VC and IL. Okay, state variables are those variables that you cannot express other variables in form of them. So for example, I'm just saying the reason IC is not a state variable is because I only need the knowledge of VC to obtain IC. So that means, therefore, we cannot take IC as a state variable. The same way we cannot take VL as a state variable. Why? Because I only need the knowledge of IL to obtain what VL is. So we cannot pick that as a state variable. The idea was we pick physical variables that cannot be expressed as a form of other variables. So since IC and VL are not state variables, we have to express IC and VL as linear combinations, of state variables, and our state variables, we say that VC and IL, because they're the ones that have got even derivatives. And the input, and our input is the voltage V of T. Okay? So how do we do that? That is what takes us to step number 3. So here you can apply either, whichever is applicable, okay? So we can apply KVL or KCL, however appropriate, okay, to obtain the IC and VL in terms of VC and IL. Remember, VC and IL are our state variables, because the idea was we found them as the ones that we can express as a derivative. So clearly in our equation here, VC has a derivative, which is dVC dt, and IL also has a derivative, which is dIL dt. So clearly they make our state variables. But because we were able to express IC as a form of VC, then IC is not a state variable. And again, because we could not express VL, we could express VL as as a form of IL, then VL is not a state variable. But we can now express IC and VL as linear combinations of VC and IL. So now how do we do that? It's very simple. That is where we apply our Kirchhoff's current or voltage law, depending on the case. So in this case, we have a node at that point. So let's say our current IL is entering, our current IR is leaving, and current IC is also leaving. So we can write at node 1, let me just call this node 1 so that somebody doesn't get confused later. So let me call this node 1. So we can say at node 1, okay, we can say the current that is entering is IL, IR is leaving, so IR is negative, IL is positive, and IC is also positive. So basically we can say IL is entering the node. IR is leaving, so IL should be equal to, I'm just writing it here so that I should be equal to IR plus IC. Because notice, IL is entering, IR is leaving, and IC is also leaving. So if I make IC the subject of the formula here, I will have IC to be equal to minus IR plus IL. So that's the equation I want to start with here. We can say at node 1, IC equals to minus IR plus IL. Now, again, let me just mention, you could use a different direction for these currents. I have no problem, but you will still get the same answer once you apply the correct Kirchhoff's current law. It will still give you the same solution. So that should not be a problem. I think you've done that in your previous classes. So now from here, we can say IC. Remember, our idea was to express IC and VL in terms of VC and IL. So IC would be equal to minus IR. So if I asked you, what is the voltage across the resistor? What is the voltage across this resistor? Now, typically, you can see that the voltage across the resistor the resistor R is in parallel with the capacitor C. So the voltage across this resistor is the same as the voltage across the capacitor. So therefore, I can say that the voltage, because I don't have VR, we are not referencing VR. We only have, again, I'll have to explain myself here. We are expressing IC and VL in terms of VC and IL. So whatever we write should always consist of VC and IL. Whatever we write in the equation of IC should be equal to VC and IL. Whatever we write in the equation of VL should be in terms of VC and IL. That's why I'm saying here, from the equation at node 1, we have IC equals to minus IR plus IL. But I have to change IR and IL so that they're in terms of VC and IL. So, of course, there's already IL here. I have no problem with that. But for IR, it's the same as the voltage across the capacitor, VC, divided by the resistance R. So here I can say this is the same as VC. Of course, minus is there, the voltage across the capacitor over the resistance. Of course, plus IL. So notice I've written IC in terms of VC and IL. So we have written IC in terms of state variables, VC and IL. Please note VC and IL, our state variables is VC and IL. Notice the idea is we are trying to come up with the state equation. The state equation must consist of state variables. That's why we are writing this. We are writing IC and VL in terms of the state variables, because that's how we'll come up with the metrics. Now, let's look at how we can now write. So IC we have done. We've done IC in terms of the state variables VC and IL. Now we need to do VL. What is the voltage across the inductor? VL. The voltage across the inductor. So in order to do that, of course, now you'll have to apply another technique so that we come up with VL. So clearly, here you now need to use KVL in this case, because now we are looking for VL. We are looking for VL in terms of VC and IL, the state variables. So how do we do that? Now you'll have to apply KVL in your equation. And you can see that if you consider a loop, the algebraic sum of currents in a loop, the algebraic sum of voltages in a loop is 0. Okay? So let's consider the outer loop. I think you have done this before. So if you had a loop, let me just draw it in red. If you had a loop like this, for KVL, you had a loop like that. That's called the outer loop. So write KVL for that outer loop. We will see clearly from KVL for the outer loop, we will write, let's start even from the inductor. It's the voltage across the inductor, VL, because we come across that. Then we are following the outer loop, not the inner loop, the outer loop. Then we come across the voltage across the capacitor. So plus VC. Then we are following the outer loop. Then we come across minus VT should be equal to 0. I don't know whether this is correct. I don't know whether I am correct. Let me check if the diagram I drew was correct. Yep. So VC using the outer loop. So we can write VL, or we can write VL to be equal to minus VC plus VT. I think that's correct. The voltage, the KVL here is correct because we are having VL plus VC minus VT should be equal to 0. So clearly, if I make, because I'm looking for VL, so we can actually now write, I can just say using KVL on the outer loop, we can say that VL plus VC minus VT, these are small quantities, should be equal to 0. And therefore, VL should be equal to minus VC plus VT. Again, notice the idea was we were to write IC and VL in terms of VC and IL. We've accomplished the IC part. Now we want the VL part. So VL in terms of VC and IL. So this is already VC. We have no problem. We have to write what is the voltage? What's the voltage at the source? I'm even writing it wrongly. It's supposed to be VT like this. Yeah? Because it was, yeah, it's VT. Okay. So now, what is VT? What is the voltage? We cannot write the output in terms of any other thing. So we'll just leave it like that. Because it's a source voltage. So let me leave it like that. Then go to the next step. So in the next step is now where we have to substitute. We have to substitute these values. I think we are almost done with this. I'll just do one more example and then I leave you. Substitute. I think I need to give these things, get equation 2. Let me call this equation 3. This is 4. This is 5. And this is 6. So substitute equations 5 and 6. And we want to make them, so we have in 1 and 2. Because we now have what IC is and we have what VL is. So IC is provided as equation 4, VL is provided as equation 6. So what do? Substitute equations 4 and 6 into equations 1 and 2. So let me rewrite 1 and 2 in the proper manner. 1 and 2 could be written as C dV what? C dV C dt. dV C dt equals to IC. I'm just writing it in the opposite direction. L di L dt is equal to a VL. So this IC, we have just found it to be equal to minus VC over R plus IL. And we have found VL to be equal to minus VC plus VT. Okay? So therefore, I can say dVC dt is the same as, I divide everything here by C. So it should be minus VC over RC plus 1 over CIL. Okay, and the IL, the T should be equal to minus 1 over L VC, okay, plus 1 over L VT. So, step number 5, step 5, I don't know whether it's step 5 or step what. My steps are mistaken. 2, 3, 4, 5. Okay. Step number 5 is we now find the output equation. So the output equation, ladies and gentlemen, by the way, notice I have written VC in terms of VC and IL. So now we have this 2 will give us, this 2 will give us the state. These are the state equations. We can write them in a matrix form. And so we have to find this output equation. The output, we already told from here that the output should be, the output IRT is the output. So we were told that the current should be output. So what is the current IR? Because it's the output. IR, clearly from your diagram, it should, the current, this is Ohm's law. The current through the resistor should be the voltage over the, should be the voltage across the resistor over the resistance itself. And we had said that the voltage across the resistor here is the same as the voltage across the capacitor. Because we are not making reference to VR, we are making reference to VC. So VC over the resistance R. So this will form the output equation. This one is the output equation. This will give us the output equation. So in a nutshell, we write this properly in state space representation. So state space representation for this electrical network is clearly, you can see we have DVC and DIL. So how do we represent those? V derivative, I think it's VC derivative, and IL. Now I have to put derivative again. IL derivative. The left-hand side of this equation should be equal to minus 1 over RC, minus 1 over RC. The other one should be 1 over C. The other one should be minus 1 over L. The other one should be, because it's 0. And this is VC. VC, and this is IL. Should be equal plus 0 and 1 over L. 1 over L of VT. VT, like that. So that's how you write the state equation. And the output equation is from this IR. So we just write IR should be equal to 1 over R0 into VC IL. Again, this is just matrix representation. I told you by now you should know how to do matrix representation. Okay, so this 2 is the solution. This 2 is what we need to find. So that gives you the answer. So I've simply just written this equation to form the state equation, which is the first one, and the output is also written here to form the second equation. So this is for an electrical network. It should be easy to do, it's only that I'm taking my time to do a lot of explanations, but it should be a very quick exercise to do. Please remember, the idea is we are following this rule. The first equation we wrote here, that you have to write your state equation as a derivative of the state variable to be equal to ax plus bu, and the output y is cx plus du. Clearly, you can now see that in our answer, this is basically, this is our derivative, okay? This was our derivative. X should be equal to, this is our a, okay? I should be writing it in red. This is our a, okay? And this should be x. So notice the variables on our state vector here, you can see, is the same as the one we have here, only that this is a derivative. Plus b u, okay? So our b in this case is this, but it's now a vector in our case because it's a small, it's a second order equation. And then this is y equals to cx plus du. So you can clearly see that we don't have a d. This part is 0. We only have cx in our output here because du is not there. So our C is this matrix, and this is still our X. So notice this is still our X. This one is our X, the vector X. It's the same, VCIL, 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 okay? So this is like just saying Y equals to CX because there's no DU in our case here. I hope that is very clear. Now, this is an example using an electrical network. I want to quickly rush through another example using a mechanical network, and then I leave you, we proceed tomorrow where I will do a more complex network for you. I will try also to give you the notes after this, but I'll send them to the class rep. However, the examples that I'll do tomorrow are not available in your notes, okay? So let me do a quick one, just a quick one, 10 minutes, because now you know what we are trying to do. Let me just do one more example today. And it says that, what time is it? Yeah, this is only going to take 10 minutes because I need to explain something. Consider a mechanical system. So this is a mechanical system. It's not an electrical system. Tomorrow I'll do an electromechanical system that combines both. So it's more complex. Consider a mechanical system. Assume that the system is linear, okay? Represent the system using state space modeling. So now I'm not going to go into those steps things. You should just know what I'm doing. So the system that has been provided here is one that we encountered a lot in physics, because it's just a spring damper system. So you have a spring, then you put some mass on it, and then you have a damping system. Okay. So the damper is also fixed. Okay. So the spring has a constant, K. This is the mass M of your system. And of course, this is the damper with a coefficient, damping coefficient given there. These are very simple system that we encountered in physics, and I think also when we were doing mechanical systems. So let's consider this to be U of t is the input. So here you have been given the input, and of course the displacement here, Y of t, is the output. So here you have been given this. So you have been asked, can you represent this system using state space modeling. I'd given you a clue previously that some of these systems, especially mechanical systems, the position can be a state variable, then the velocity, which is a derivative, is also a state variable, and even to extend further, the acceleration can also be a state variable. Now, for those of you who remember your mechanical systems properly, or even the physics, we can say that the system equation is, you remember how we come up with this system equation? It's from that rule, F equals to, is it F equals, this is third law. This is the third law for, why am I forgetting the name of this guy? Is it Newton's third law of motion? Okay, so the system equation anyway is written as, again, y is the output, so we can write this equation as my. This is in several books. I think you can find that. For the acceleration, for the velocity, we can have the damping coefficient y plus ky for the position equals to u of t. Okay, I don't want to write u of t. But typically, this is how you can represent the system equation. There's so many, it's derived in so many books, how you come up with this system equation. You can look at it. No problem. But now we have to get the state variables. State variables. How do you get the state variables? So let's define, let's just say, let the state variables, clearly you can see this is a second order differential equation. So let the state variables be, so it means we'll have two state variables because these are second order differential equation. Let the state variables be x1 of t and x2 of t. Just arbitrarily, because we haven't picked what those state variables are. But now, from the system describing the equation describing the system, what is x1 of t? And what is x2 of t? So our first state variable should be a quantity that you can also differentiate. So if it's a position, then the other state variable should be a velocity. Okay? So in this case, you can see that you can take the position from this. You can actually even look at this, ladies and gentlemen. Let me give you a hint for those of you who are forgetting something. From the system describing the equation, you can see this is position. Because a spring damper system is if you pull the spring, if you pull the mass down here, it will extend by a certain value, or it will be displaced. So that is the position. And then the derivative of that is the velocity. And of course, this is the acceleration. So the acceleration is associated with the mass. The velocity, meaning the acceleration affects the mass or is affected by the mass. The velocity is affected by the damping coefficient, and the position is affected by the spring constant. That's why the system equation is usually like this, because the position is affected by the spring constant for your system, the velocity is affected by the damping coefficient, and the acceleration is usually affected by the mass. Okay, so clearly you can pick because this is a second order, we only need two state variables, which can be position and velocity. So here you can say the first state, let the first state variable be y of t, which is basically the position or the displacement for that matter. And then the derivative of it is now the other state variables, and that is the velocity. This is displacement. Some people will be wondering what is position, displacement, and something like that. So clearly, once you have those, you have already known, and the minimum number of state variables is 2 because we have a second order differential equation. So now we can quickly just rush through this and obtain the state representation. How? For this case, it's pretty easy because we can now say that if I get the derivative of x1, so see, if I get the derivative of x1, it's the same as getting the derivative of y, meaning I'm getting the derivative on the left-hand side, so I have to get the derivative on the right-hand side. Now, if I get the derivative of this right-hand side, you can see that that is equals to x2. I'll repeat that. I'm trying to obtain the derivative on the first, because the equation is such that we have to get x bar equals to ax plus bu. So we have to get a derivative. We must have a derivative on the left-hand side. The first equation that we solved here, we were already lucky that our equation had derivatives. So we only made this we made this to be the left-hand side and this to be the right-hand side. But in our case here, we don't have derivatives in our system equation. So we get the derivative on the left-hand side, we have to get the derivative on the right-hand side. And of course, y bar, or the derivative of y, is, if you look at the velocity equation, is the same as x2. How about the second equation? Let's get the derivative on the left-hand side for the second part of the equation. Then it means we'll have to get double derivative of the second part. And what is this double derivative? You can obtain it from here. You make this the subject of the formula, because you have y, double derivative of y, or of the displacement, is here. So we can make it the subject of the formula and we write it here. So if you make it the subject of the formula, meaning all these things will go to the left-hand side, so it will be a negative k over m. I know some people will be struggling. Let me do this the long way. So it's like saying my bar should be equal to minus ky minus by bar. I hope that's clear. So y bar should be equal to minus k over my minus b over my derivative. Okay, that's now clear. But notice y, I want to write it in terms of x. You can see here, this is the same as minus k over m. What is y? Y from the first equation here is x1. Because the equation states that we have to be the derivative of x should be in the form of ax plus bu. And of course, y should be cx plus du. So that's why everything has to be in terms of x1 and x2, which are your state variables. Everything has to be in terms of x1 and x2. That's why even the y here, I'm changing it so that it's in terms of x1 and x2. And y is x1, so minus b over m. Y bar, not y bar, sorry. The derivative of y is x2. So that's why I'm saying my equation here should be minus k over m x1. So because I've explained that, we can now write it properly. So minus k over m x1, x1 minus b over m x2. Is there something? Oh, I forgot the u part. So please remember, I forgot the u. So plus 1 over m u. Okay, so I'm just making the double derivative, the acceleration here is made the subject of the formula in this equation, and then you replace it here. So now you can see that I have derivatives. So you can see that these are the x's on the left hand side. You can see that these are x bar. Then you have some terms with x1 and x2 on the right hand side, which is how the equation should look like. So now you can actually write that output, that state equation. So if you have it like that, then you can now write the state equation properly and say that the state equation, let me just write the output equation first before I write the state equation. So the output equation is, what is the output? we have been told that the output is y. And what was y? The output is y. And what is y? It's x1. So we just say that y, which is we have been told is the output, is the same as x1. Okay, so now we can write our state space representation. State space representation. So in our state space representation, we can use this, we can say x1 bar, x2 derivative, let me use the right terminology, should be equal to the coefficient of x1 in the first equation is 0, there's nothing there. And in the second equation, it is minus k over m. The coefficient of x2 in the first equation is 1. In the second equation, the coefficient of x2 is minus b over m. So this is in terms of the state variables x1 and x2. But because x2 has another variable in terms of u, which is the input, so that is, so we can write 0, 1 over m u. Okay, so this is like saying this is your x bar equals to a x plus b u. But b is now a vector. It's not really a matrix because our system is second order. Had our system been third order or fourth order or more complex, it would be a complete matrix. And then we can now write another equation for the output using these two. Again, remember the output equation must also be written in terms of the state variables. So the output equation would just be y, the output equation will be y equals to, the coefficient of x1 is 1, the coefficient of x2 is 0. So we have to write it in terms of the state variables also. So you can see this is what we had done previously. It's in terms of cx plus du. So clearly this term here is 0. It's not there. That's why we don't have it. So we only have cx. But this is the representation of that mechanical system in state space. That is the representation in state space. So ladies and gentlemen, I'll end this class here. We have a few minutes to go unless there's a question. So tomorrow I'll do one example which is very critical. It's not in your notes. I'm going to send the notes to your class rep immediately after this class, but I'll do an example that is not available in your notes. So I'll hope that, and it's more complex, and it's the one that opens your eyes more on state space representation. So see you tomorrow at 2 p.m. Unless there's a question, we'll end the class here. Kama kuna mtu ako na swali, please ask now. Yes, Alphonse.
Yes, excuse me, sir. In step 5 for the first example, we were talking about the current through the resistor, but then in the state representation, we said the current through the inductor.
Wait, let me go back. You said in step 5 of the, we said?
The output equation was.
The output equation, we said, look at the equation, Alphonse. Let's look together at the equation. It says, given the electrical network, find a state space representation if the output is the current through the resistor. So the output is the current through the resistor. Sindio?
Yes.
So let's go to step 5 then. Step 5 says, find the output equation. So you see the output equation is IR, which is the current through the resistor. We know is typically using Ohm's law should be VR over R. See, we agree? Is that okay? Alphonse? He's gone silent. I wanted to understand his question. Alphonse?
Hello, excuse me.
Yes.
I think in the output equation in our final answer, we indicated IL instead of IR. Yeah, right there.
Oh, Thank you. This is what he meant. Okay. This is IR. Thank you guys. It's IR because it's the output. The output is IR. Notice that I'm writing even the output matrix here is 1/R0, but we have to write it also in terms of the state variable. So it's IR. Yeah. Thank you. If that's what he meant, that's I thought he probably didn't understand how I was using VC instead of VR, but I think it's my mistake. This is IR, not IL. Thank you. Okay, any other question? I have to stop sharing to see who's asking.
Excuse me, I had a question about how we selected the state variables of the first example.
How we selected the state variables of the first example. Okay, so what is the question?
We made equations of IC equals to C derivative of VC and VL equals
Let
to
me go back. Yeah.
And the next statement, you stated that IC and VL are not our state variables.
Yes.
But now if VC and IL are our state variables, and now the derivatives of those state variables, aren't they considered as state variables as well?
Okay, if I get you correct, it's here. IC and VL are not state variables, meaning this is not a state variable and this is not a state variable. Do we agree?
Yeah, but now our state variables, they're derivatives.
Our state variables are derivatives.
No, I mean the derivatives of our state variables, we stated that can be considered as state variables too.
Yes, the derivative of a state variable is also a state variable. Now notice, it is VC because we already have a derivative. We have VC, a derivative of VC as a state variable, meaning VC can be a state variable. Sendio, here we have a derivative of IL. So it means IL can be a state variable. So the state variables are VC and IL, not IC and VL. The state variables is the voltage across the capacitor and the current through the inductor, not the current through the capacitor, neither is it the voltage across the inductor. So I don't know whether we see it. So because we already had an equation here that has got a derivative, then we can use those as the state variables, meaning because VC already has a state as a derivative here, VC can qualify to be our state variable. And because we already had DIL dt, then IL can be a state variable, but not IC, not VL. What's your point? Again, maybe it's me who doesn't understand your question properly.
And now for the second question, for the second example we've done.
Yes.
We've stated now x2 equals to derivative of x1.
X2 is equal to derivative of x1.
Yeah, as our state variable.
Yes, because you see, the idea is we had said let our variables, we don't know what they are, what quantities they are. We're just saying let us have two state variables because we have a second order differential equation. So our state variables are x1 and x2. But what is x1 in terms of our system and what is x2 in terms of our system? And I've told you that in mechanical systems, we usually pick things like position and velocity and acceleration as the state variables. So because we said let x1 and x2 be our state variable, our system consists of position. Because this is a pendulum, not a pendulum, but this is a spring mass damping system. What changes is, if you extend it, what changes is the position or the displacement. So that displacement becomes our state variable. Then we know that if you get the derivative of a state variable, you still get another state variable. So x1 is now the derivative of the first variable, which was position or displacement. So velocity also becomes our state variable. So please note what I'm saying is derivatives, variables and their derivatives can be a state variable. variables and their derivatives can be a state variable. So if you have a variable y, if you've got the derivative of y, that can also be a state variable. If you get the double derivative of y, that can also be a state variable. So it's only that in our second example, you can see from the system equation that you could pick this as a variable because it has a derivative. You can see it in the system equation. If this was a third order, we would even pick acceleration as another state variable. But in our first example, the question itself had already given us a derivative in it. So we only needed to know that if VC has a derivative, which is dVC dt, then VC can be a state variable. The same way we already had dIL dt as, so it means it's like IL derivative. So it means that IL can be a state variable. But IC and VL cannot be state variables because we could represent them as combinations of VC and IL. I'm not sure whether we are on the same page.
Yes, it's okay.
Yeah. So if in case you still have any doubts, even after reading the notes that I'm gonna send you, then maybe we can still engage further when you see me, or you can drop me an email and I'll try and explain further. I hope that's fine. All right, so ladies and gentlemen, our time is up. I don't know if there's any other burning question. I see a lot of people have logged out already, but we'll end here. We'll meet tomorrow for the next session, and then we do our CAT next Monday. So have a good day and see you. Bye-bye.